Alright, so let's apply what we have learned to the Bayesian linear model. Note that in this case we don't talk about the Bayesian Gaussian linear model as in previous lectures, and the reason is that we don't need the Gaussianity assumption. The Lmsc estimator depends only on first and second order moments. It doesn't depend on the specific shape of the PDFs. So x is given as always by h theta plus noise, where theta and w are independent, and we are given the data, matrix H, the prior mean and covariance of the parameters, and the covariance of the noise. The mean of the noise is assumed 0 as always. Okay, so the Lmmc estimator can be found using the very same techniques that we have used earlier in this lecture. So I suggest that you stop the video at this point and try to show that it is indeed given by this expression here. Okay, I hope you made it. We just need to start by the expression that we know for the Lmmc estimator and obtain these quantities here. Let's start by the mean of x, and we just substitute the definition of x here and take these expectations, and just by noting that the mean of w is 0 and results in h times mu theta. The covariance of theta and x can be found just again by using the same expression and applying the properties of the covariance that we saw or we reviewed earlier in this lecture. Note that the covariance of theta and w is 0 because they are independent and therefore uncorrelated. The covariance of xx follows in a similar way, but now in order to perform this step we need to use the fact that theta and w are uncorrelated, and therefore the covariance of this sum equals the sum of the covariance matrices. And one can again apply the same properties, and this is what we obtain. Just substituting these quantities here, we will recover this expression that we needed to show. To obtain the performance, we can apply the general expression for the covariance of the error of the Lmmc estimator and substitute again these values, which will yield something like this. And if we want something fancier, we can apply the matrix inversion lemma to find that this covariance is given by the inverse of this matrix. It is always good to perform some sort of sanity check, just to make sure that we are not totally wrong. So for example, one can think what happens if the data is not very informative, if the noise has a very high power, right? So in that case, this inverse will be small, and therefore this matrix will be small, will perhaps close to 0, and what we find is the c theta theta inverse inverse, right? And therefore c theta theta, and therefore it means that in that case the covariance after seeing the data, the covariance, the uncertainty after seeing the data is roughly the uncertainty before seeing the data. So it makes sense, and then the sanity check is passed. We will now develop a calculus of Lmsc estimators, which will prove instrumental for deriving sequential Lmsc estimators in the next lecture, and eventually the Kalman filter. So let's start by this property that is called equivariance to linear functions of the parameters. So here this property states that the Lmsc estimator of a linear function of the parameters equals the linear function of the Lmsc estimator of the parameters. Be careful with the dimensions, since this has length m, then G needs to have m columns, but otherwise G is arbitrary, it can be any matrix. As an exercise, I suggest that you stop the tape and prove it. It can be done in just 1-2 lines. Okay, so I hope you made it. The solution is like this. We just apply the general expression for the Lmsc estimator, so it is the mean of what we want to estimate plus the covariance of what we want to estimate and the data, inverse of the covariance of the matrix of the data, and x minus mu x. Now we just need to apply the properties of the expectation, so this G comes out, and also the properties of the covariance, so this in G comes also here to the left. We can then take G a common factor and recognize that what we have in brackets is just the Lmsc estimator of theta given x, which completes the proof. The second property is what we call here the invariance to invertible linear functions of the data. So note that now the functions need to be invertible, okay? So not like here, okay, there were any linear function. So this property states that the Lmsc estimator given a linear function of the data is just the Lmsc estimator given the data. Note that since the function, this linear function needs to be invertible, then this matrix F is needs to be square, of course. Okay. So again, you may stop the video and prove it. It's very simple. Okay, so we again apply the general expression for the Lmsc estimator, and now here we have the covariance of theta and fx, and here the covariance of fx inverse, right? And this is our theta minus its mean. Okay. So here applying again properties of the covariance, this f comes out to the right with a transpose, okay, and here it comes to both sides because this is the covariance of a vector and itself, okay. And now what we can do is just to use the fact that this f is invertible, right, and therefore the inverse of this matrix here is f transpose inverse times the inverse of the covariance times the inverse of f. Okay, and now one can just cancel these matrices here, and what we are left with is the Lmsc estimator of theta given x. Okay, So this is quite an interesting property, because it really captures what is the nature of information. Okay, so as we can see, we are using an invertible function of the information, and whenever we use invertible functions on some vector, it means that we can recover the vector before applying the transformation. So that means that no information is destroyed, right? So it would be a problem if the estimator changed by applying some transformation like this on the data. That would mean that the estimator is not optimal, right? Because there is exactly the same information in fx as in x. Okay, so now we are also learning a little bit of information theory. Okay, so now let's see some implications of these properties. Here there is an exercise that you can try to solve. It's very simple. The vector of parameters is defined by two blocks, right? So two sets of parameters, and the point here is to show that the Lmsc estimator of this vector is just the result of stacking the Lmsc estimators of each block of parameters. And the proof is again very simple. Just need to be careful with how you define the matrices. Okay. So another exercise is to apply the equivariance property from the previous slide to show that the Lmsc estimator of the sum of two parameters equals the Lmsc estimator of one parameter plus the Lmsc estimator of the other, okay, vectors of parameters. So again, you can try to solve it. Okay, here's the solution. The idea is that this sum of vectors can be written as this linear function of the result of concatenating vertically these two parameter vectors. Okay, and by the equivariance property, this matrix comes out, and this is what we recover. Okay, so one just applies what we have seen here, okay, to obtain this expression, and just by multiplying this matrix and this column vector, this is what we obtain. Okay, and this concludes the proof. So very simple application of the equivariance property. And now let us use the invariance property to show that if we use two data vectors to estimate a parameter, and we add a scale version of one of these vectors to the other, then the Lmsc estimator does not change, right? This is like reminds us of, for instance, the rank of a matrix, right? If we add to a row a scale version of another row, then the rank doesn't change. So it's like similar here. Note, be careful with the notation. Again, whenever we say Lmsc estimator of theta given x1 and x2, what we mean is the Lmsc estimator of the vector that results from concatenating vertically these two vectors here. Okay, so I mean, just And this is just a way of writing it in a more compact fashion, but I mean, we prefer the notation of where we put all our data as a single vector. Okay, so the solution is again very simple, and the Lmc estimator of theta given this is as per this notation, precisely this one. Okay, and now one can just write this vector as this matrix times this vector over here, right? And note that this matrix is invertible. Okay, that can be easily seen, right? For instance, you can see that the determinant is 1. Okay, so no question that it is invertible. And now we can apply the invariance property to just get rid of it. Okay, so the proof is again very simple. Perhaps the only difficulty would be to realize that or to find this matrix. I mean, what I do in these cases is just to write sort of an empty matrix and write here the vector, the desired vector, and I just complete the entries. I mean, it's a pretty simple task. In fx as So let's see some implications of these properties. Here we have one exercise where we where we have a vector of parameters defined by two subvectors, okay, stacked vertically, and we need to show that the Lmc estimator of theta is just the result of stacking the Lmc estimators of each of these subvectors of parameters. So again, please try to show it. Okay, so I mean the proof is very simple. You just need to be careful with the matrix. I mean the vectors defined by blocks and matrices. So it's quite straightforward using the same rules as we saw earlier. So now let us apply the equivariance property to show that the Lmc estimator of the sum of two parameter vectors equals the sum of the Lmc estimators of each Okay, so let's see some of the implications of these properties. Here we have an exercise where the parameter vector is divided in, or is defined by two blocks, so two sub-vectors stacked vertically. And the goal is to show that the Lmsc estimator of theta is just the result of stacking vertically the Lmc estimators of each subvector. Okay, so this is very simple. It just needs to be careful with the block notation. Okay, so the next exercise is to use the equivariance property to show that the Lmc estimator of the sum of two vectors of parameters equals the sum of the Lmc estimators of each parameter vector. So again, it's very simple. Okay, so this is the solution. We can express the sum of these two vectors as this matrix times this vector. Okay, that is obvious. And now, if we just apply the equivariance property, this matrix comes out, right? And one can now use what we have seen here to write this Lmsc estimator in this way. And one just needs to now multiply this matrix and this column vector to obtain this, which completes the proof. The next exercise is to use the invariance property to show that if we add one of the vectors that we are using to estimate the parameter to the other, then now let's see some of the implications of these properties. Here we have an exercise where the parameter vector to be estimated is defined in terms of two blocks, so two subvectors that are concatenated vertically. And the goal is to show that the Lmc estimator of theta is just the result of stacking vertically the Lmc estimators of each of these vectors. Okay, so again, it's very simple. You just need to be careful with the block notation. Okay. Okay, so now the next property, or the next exercise, is to use the equivariance property to show that the Lmc estimator of the sum of two parameter vectors equals the sum of the Lmc estimators of each parameter vector. Okay, so just again suggest that you try to do it first. And this is the solution, and the idea is to write the sum of parameter vectors as this matrix times this column vector here, right? So it is obvious that these two things are the same. And now by the equivariance property, this matrix comes out, okay? And now one can use this fact here to write this Lmc estimator in this way. So then it remains only to multiply this matrix and this column vector to arrive at the desired expression. Okay. And now for the next exercise, let us introduce some notation. The Lmmc, whenever we write the Lmmc estimator of theta and given x1, comma x2, this means the Lmmc estimator of theta given this vector that results from concatenating these two. So this is just a matter of writing things in a more natural fashion, but for our expressions, we prefer to collect all the data in a single vector. In the same way as throughout the course, we assume that the parameter vector is, the data is a vector, right? You have in your application, your data is a matrix or a tensor or whatever, just vectorize it and that's it, right? So the idea is to show that the Lmmc estimator doesn't change if we add a scale version of one of these vectors to the other. Okay, so this reminds us of properties, for instance, of the rank of a matrix, right? Where adding a scale version of one row to another row doesn't change the rank, right? So a similar thing occurs here. Okay, so here this one is just slightly more tricky than the previous ones. By this notation, we just write this Lmmc estimator in this way. And now we just need to realize that this vector can be written as this matrix times this vector here. So this is, it is easy to see that multiplying these two, this matrix and this vector yields this vector. It's perhaps a little bit more difficult to find this matrix given this vector, but what I do is in these cases is to write first an empty matrix here, write this vector, and then complete each row, right? So it's pretty easy. And now we can just need to recognize that this matrix is invertible, right? This can be seen in multiple ways. Perhaps the simplest one is to note that the determinant is 1, right? It's the product of the diagonal entries because this matrix is triangular, and therefore it is invertible. So as per the invariance property of the previous slide, this matrix here can be removed and we recover the Lmmc estimator of theta given x1 and x2. So now let us prove a property that constitutes the basis of the so-called innovation trick, which is a very smart technique that gives rise to the Kalman filter, and that we will be using in the next lecture for sequential Lmmc estimation. So the property says that the Lmmc estimator of a vector given two uncorrelated vectors, that is really important, that they are uncorrelated, is the sum of the individual Lmmc estimators given each of these data vector. Note that there is an additional term here. This is, the intuitive reason for this term is that the Lmmc estimator corrects for the mean, right? And therefore, if we add two Lmmc estimators, we would be correcting for the mean of theta twice. So the effect of this term is to cancel one of these corrections, so we have only one. But it is important to be careful because it's easy to forget about this term here. So again, I suggest that you try first on your own. Okay, here is the solution. As per our notation, this Lmsc estimator can be written in this way, and by the general expression for the Lmsc estimator, this can be written like this. Okay. So now one can just apply the properties of the covariance that we have seen or reviewed at the beginning of this lecture. Okay, so this covariance here becomes is a block matrix with these two blocks here, and this covariance has these four blocks. Okay. Now one can just note that since x1 and x2 are uncorrelated, this block and this block are 0. Okay, and therefore we can now invert this matrix, right? This is a well known fact in linear algebra. The inverse of, or the blocks, the diagonal blocks of the inverse of block diagonal matrix are just the inverses of each of the diagonal blocks. Okay, so this also takes one line to prove this, so trivial actually. So now one can just multiply this matrix and this matrix here, okay, and that yields this term plus this term. So here we see that this expectation of theta plus this is the Lmsc estimator of theta given x1. However, this is to find here the Lmsc estimator of theta given x2, we would need an additional mean of theta. So what we do is to add and subtract the mean of theta, and therefore we just arrive at these two terms here, and this concludes the proof. So let's wrap up. Remember that we define the Lmsc estimator as the best affine estimator in the BMSC sense. Okay, be careful and remember that although we have the word linear in the name of this estimator, it need not be linear. It is linear only when the means of the data and parameters are 0, right? But in general, it is affine, and it depends only on the. It can be obtained just by using the first and second order moments. So in general, or in most cases, it will exist, right? So the only possibility for this estimator not to exist is that these first and second order moments are not finite, right? So as you may know from probability theory, for some distributions the mean and the covariance are not finite, right? So for instance, for the Pareto distribution with certain parameters, but I mean, in most cases, for most distributions that we encounter, these moments are finite, okay? And therefore the Lmsc estimator exists. The main benefits of Lmsc estimators are that they lack the main limitations that we saw for MMSC and maximum a posteriori estimators. Specifically, we don't need integration as in MMSC, and we don't need optimization as seen maximum a posteriori estimators. The optimization that was required was done in the derivation of the general expression for the Lmsc estimator, but in any problem we just apply that expression, so we are done. No need to optimize for each specific problem. And as we said, we don't need to know the PDF. It's enough to know the means and covariances. So it's much more applicable than MMSE and maximum a posteriori estimators. We saw quite a few properties. The first one is that it is affine. So this implies that it is easy to compute, right, and to analyze, unless perhaps the covariance matrix of the data is very large, right, because we need to invert that matrix, and inverting very large matrices is computationally problematic. But I mean, for moderate-sized problems, it is easy to compute. Okay, and despite the fact that we restrict ourselves to affine estimators, it turns out that I mean, sometimes the Lmsc estimator is also the MMSC estimator, right? Specifically when the MMSC estimator is linear, right? And we saw that that is not such a strange case, right? Because, for instance, if x and theta are jointly Gaussian, then the MMSC estimator is linear and therefore coincides with the Lmmc estimator, right? So also another very important property is this one: the error is uncorrelated with the data. Okay, we also said that one can interpret this the Lmmc estimator as a projection in vector space of random variables with an inner product, which is given by the expectation of the product of random variables. But I mean, of course, that was just perhaps an abstract perspective that is, we said, it's not really necessary to understand the contents of this course. And additionally, we also proved equivariance, invariance, and additivity of the Lmmc estimator. We will be using these properties, all these properties, extensively in the next lectures. And what is coming up is sequential estimation, right? So what happens if we don't receive all our data at once? We receive data little by little as it occurs in great deal of practical applications. So this is actually very interesting. I hope you also look forward for the next lecture. Okay, so thanks for your attention. See you in the next lecture.